Hey everyone, my name is Rocio Vidalis, and this is my lab 3 for my Physics 1 class, and it will be about a black hole. So after I introduce this lab to you, I'll show you my 2 computational models and give you some further understanding. This lab is split up into 2 sections. In the first, we'll observe a star's orbit nearby the black hole, and we'll use formulas to find the black hole's mass. Then we'll use that mass for part 2, in which we'll observe a spaceship's orbit nearby, and we'll use all of this to determine the initial velocity needed to escape the black hole using the spaceship. And I'll show you all of this using GlowScript coding. Of course, before we start, there are some fundamentals you must know, such as the momentum principle. dp dt is equal to dp dt parallel plus dp dt perpendicular. We also have the velocity update formula, which is final velocity is equal to initial velocity times net force over mass times change in time. We will also be using the position update formula, where final position is equal to initial position times average velocity times change in time. But since we are using non-constant forces in this lab, we'll change the velocity average to final velocity. And this will give us an answer that's not entirely precise, but it's as close as it gets. And then we will also be using the universal gravitational force. So in our part 1, the system is going to be the star. Part 2, the system is a spaceship. For both, the surroundings will be the black hole. And our results will be that the black hole's mass is 1.99 e to the 34 kilograms, and the initial velocity is shown through the vector shown on the screen, and it is in the units of meters per second. And in the next few slides, I will be explaining to you the code I used for the first computational model, but this is what it ends up resulting as. You can see the orbit of the star around the black hole. So first I must put in our initial conditions, which will have our gravity and the mass of the star that we are given, and delta t accounts for the number of seconds within a year, and we start at 0 seconds. So now that we've input the necessary variables, we will try to find the black hole's mass by calculating the net forces. On the bottom of the left picture, we have written that the net force is equivalent to the change in momentum from Newton's second law, and to the right we have our formulas working together to find the following. These are the results. The net force and its components, the parallel and the perpendicular, and our black hole's average mass is 1.99 e to the 32. Similar to the previous part, I have my initial conditions, this time adding my black hole's mass and using a lot of the universal gravitational force formula to find things like those in line 93, where the force of the spaceship on the planet is equal to the negative gravity times ship and planet masses over the distance between the ship and planet, all times the unit vector. Through trial and error, we are able to determine the initial velocity that the spaceship, which is the line in magenta, that it needs so that it doesn't hit the star, which its orbit can be seen by the blue line, and so it doesn't get sucked in by the black hole. And from these 2 codes, you can see that as the planet gets closer to the black hole, the mass of the black hole also increases, and vice versa. And I also must mention that this is very approximated because there's a lot of rounding, and the mass of our black hole is average, so it's bound to change in real life throughout. Okay, so after this lab, you might be wondering if there's any difference between the net force components, the perpendicular and parallel, and the rate of change of momentum, which is dp dt. Well, there's no difference between those because Newton's second law states that net force and the rate of change of momentum are the same. And what if you also wanted to orbit around the black hole? Well, for this, you'd have to change the initial velocity to be negative 2.51 e to the 6th, and with a y velocity of 1.38 e to the 7th meters per second. I hope you enjoyed this lab. Thank you.